Hey, Bio1 students, Mr. Yance again. Welcome back to another set of notes. So we're going to pick up where we left off with meiosis. And I know we did this slide already in the last set of notes, but I kind of like to start here because this bottom part of this page is what we're be talking about. What is that cell division involved in sexual reproduction? Because we got to get this egg and sperm to the right number of chromosomes. So a little background. So I'll go through the background today and then show you a little bit about the phases, because a lot of it's like mitosis, but there is some differences. And then the last set of notes that will wrap things up will be why we divide the cell twice. So meiosis is different in a couple different ways. Okay, so first of all, let's talk about normal members. Means that all normal members of a species, and when I mean normal, that's kind of a vague term. What is normal? Good question, right? Normal is the right chromosome number. So I know that we're set at 46. I know there's people that have 47, 48, 45, 44, but they have diseases. They have some issues. So that's what we mean by normal members, okay? It just means they have the right chromosome number. Chromosomes always occur in pairs, because if you think about it, I get half of them from mom and half of them from dad for a total of 46 in humans. So we get 23 from each parent. Now, these chromosome pairs are identical in form and arrangement. We call those homologous. Doesn't mean they carry the same information. Might have blonde hair and black hair, may have green eyes, blue eyes. It just means they're the same size and the same location. We have the same genes for hair color or eye color or whatever, okay? In humans, we have 46 or 23 pairs. Now, this is really critical to understanding meiosis. We have a haploid number. Just remember, HA, half, is half of your diploid. So the haploid number for humans is 23. The diploid or diploid number is 46. So we use a symbol. The little n means haploid, 23. If you look down here, it says, I put a 2 in front of that n. I take whatever the n number is times 2, and that gives me my diploid number. So on the test, I ought to be able to give you either one of these. So I say, okay, a zebra has a haploid number of 25. Its diploid number is 50. Or I could go the other way. A tulip has 90 chromosomes. That would be the diploid number. The haploid number would be 45. Everybody with me? So, that's what you have to understand. So remember those, because those are important to meiosis. You only have a diploid number in mitosis, but with meiosis, we're going to go back and forth between those. So here we go, okay? So meiosis, by definition, is a special kind of cell division that reduces the chromosome number in egg and sperm cells. The purpose of meiosis is to produce these gametes that have that haploid number, half the number you start with. The reason for that, remember, is so when the egg and sperm come together, I get the right number in the final tally when we're done. All right, now, meiosis, I'll explain this later. Meiosis has two parts. It has Roman numerals. So it has the same names: prophase, metaphase, anaphase, interphase. A lot of that's all the same. But when you see a Roman numeral after prophase 1, prophase 2, that tells me I'm meiosis. If I just see prophase, that means I'm in mitosis. Hope that makes sense. Okay. Now, a lot of it's the same. In interphase, I have chromatin, I have a nucleus, I have a nucleolus, the cell's doing its normal thing. I go through G1, S, G2, I duplicate my DNA, cell grows and matures, all's well. It doesn't matter if it's an egg, sperm, or blood cell, okay? Interphase is the same in meiosis. Now, when we get into prophase 1, things start to get a little bit different. We got some new terms. Yeah, we still, chromatin turns into chromosomes. So all this haphazard mess up here will turn into these chromosomes. And we have an early and late prophase 1, just like we do with prophase and mitosis. The centrioles move to opposite poles. The spindles attach. We're doing the same thing. And you'll notice that I made 2 of these orange and 2 of them green to show you that in this illustration, I have 4 chromosomes, 2 from mom, 2 from dad. Okay, so that's all that means. All right. So a lot of this still is the same, and here's where it's going to get a little bit different. I have a new term. Since I have 4 chromatids coming together, you saw that in that last picture, then we call that tetrad, because as all of you know, tetra means 4, right? And the process that joins those chromatids together is called synapsis, all right? So really, we're still doing pretty much the same thing. Chromosomes line up at the middle in metaphase 1. We still have a diploid number, a total number at this point. You'll see that here. There's my chromosomes lining up at the middle. The spindle's attached to the centromere. Everything's the same as mitosis until we get to the next phase. Here's where it gets different, okay? And you'll notice in my notes there, I made it huge in big print. Put a star beside it, circle it, underline it, do whatever you need to do. This is the phase that makes meiosis different than mitosis, okay? So in anaphase 1, I'm going to go from a diploid number to a haploid number. So instead of pulling my chromatids apart and getting the same number in both cells, the homologous chromosome of each pair, remember we have a tetrad, we're going to pull them apart as a pair. Okay, so what you see here, let's go back to this slide. I have 2 green, 2 orange, 1, 2, 3, 4. But when I pull them apart, one's going to go this way, this one's going to go this way, vice versa. 1, 2, 1, 2. I went from 4 to 2. If this was a human, I go from 46 to 23. Hopefully that makes sense, right? And that's the big difference. I've reduced my chromosome number in half. I went from a diploid to a haploid. That is what makes meiosis special. That is what makes meiosis its own little identity. Okay. Now we're going to divide the cell. Cytokinesis 1, just like we did in mitosis. I divide in 2. I have 2 daughter cells, but the difference is my daughter cells have a haploid number. Okay. Now here's the other difference. I'm going to divide again. So I'm going to take those 2 daughter cells. I'm going to go right into prophase 2. I still can see the chromosomes. The chromosomes are going to line up at the equator. This is going to be just like mitosis. I don't need to divide the chromosomes in half again. I want to keep the chromosome number the same now. So the chromatids are going to pull apart, and anaphase is going to separate them. Telophase is going to divide it. Now I end up with 4 cells. So I start out with 1, have 2 daughter cells, but the difference is they have half the number they started with. And now I'm going to divide them a second time and get 4 cells with that still same number. Okay, I don't change the number again. Okay, so really it's meiosis 1 and it's anaphase 1 where we get the big difference. Okay, now the question might become, why 4 cells? Why don't we just divide like we do mitosis? Why do I need to divide the cell twice? Let me explain that a little bit. So it's got to do with the egg, or what we call the female ova. Okay, so I have my first division, and I'm going to divide again, and I'm going to get an egg or an ootid, kind of a funny name, over here. Now, here's what happens in a female. A couple things. I'm not going to get into a lot of detail here. We could do that later when we talk about that in my Bio 2 class, or you take my anatomy class. We'll talk about human reproduction, more in detail. But here's the deal. In a female, now, number one, I hope you know this by now, you're high school students, a female is only going to produce a set number of these in her lifetime. And it's in a monthly cycle called the menstrual cycle. And she has a set number she's going to produce and a set time of her life that she's going to be able to make reproductive cells. Okay? In males, that's not true. We produce them throughout our lifetime. Now, here's what's weird about a female. Is these 3 cells, I have 4 daughter cells, but 3 of them donate their cytoplasm and die. Only 1 of the 4 live. And it's a megacell. It's the biggest cell in the human body. It's the only cell we can see without a microscope, because a egg or ova is actually 4 cells combined into 1. The reason for that is because that we need that extra cytoplasm for that egg or that ootid to live and do its thing. That's what's important with that. So when that egg is it takes a while for the umbilical cord to hook up and for the mom to start to feed the baby. So before we can get to that state, we got to have that extra energy, that extra cytoplasm, so a cell can divide and become an embryo. Okay. The male, that's not true. All four live, all four are equal in size, and they all have the ability to fertilize the egg, and they're a lot smaller. Okay. And they develop tails and are motile. Okay. Now, the other thing that's interesting here is these three die. So think about this. We never think about this enough, I don't feel like. But we are very fortunate that we exist because we were the one egg that lived and we weren't one of these polar bodies, right? And we were one of these astronomical number of sperm that were able to fertilize that one egg. So really our existence is pretty impressive when you look at it that way. All right. Hopefully that all makes sense. We will review all this. I'm going to go ahead and put the notes online so that you guys can look at them. We'll have a test when we come back. We'll review for a day or two, and then when you're back, we'll take a test over all this. All right. Hey, have a great day. Stay safe, and we will see you on the next set of notes for next chapter. See you. Bye.